Okay, so yeah, welcome back, everyone. I'm gonna be speaking for at least probably a few weeks on the generalized Ricci flow and the relationship to generalized complex geometry. So far, I mean, let's just maybe recall a bit what had been going on before we transition to generalized complex geometry. We were studying the generalized Ricci flow. dg dt is minus twice Ricci g plus 1/2 h squared, and dv dt is minus d star g h, and h is some background h plus dB. And we discussed various results, including packaging these together in this sort of more generalized form. Where this script Ricci was this sort of generalized Ricci tensor. Okay. And then we proved some basic structural properties. And then we had these nice series of lectures sort of giving us a nice introduction to generalized complex geometry. So the question now sort of is, how does generalized Ricci flow interact with complex or Hermitian or generalized complex and generalized Kähler geometry. Okay, so broadly speaking, this is the approach you want to take. And I just sort of want to emphasize here and throughout that, I mean, there are some nice connections already between this equation and different pieces of generalized complex and generalized Kähler geometry, but I think there's probably a lot more sort of very basic connections yet to be discovered, most likely. But so the starting point, so to begin, I just want to recall a few things about Kähler-Ricci flow. So here I'll talk about it in a completely classic way. So I start with M2N Gj, a Kähler manifold. So this means that G and J are, J is an integrable complex structure and G is a Hermitian metric, and omega is Gj. And the Kähler condition is d omega equals 0. Okay. And well, in this setting, I'll also define a sort of a new curvature object. So rho xy.
So the notation Gj is just contraction in the first entry, right?
Yes. Yeah. I should probably, here right away ask for a blanket forgiveness of maybe signs and certain conventions and factors of two, but I'll do my best. Yeah. So rho xy is 1/2 rxy jei, where this r is just the usual curvature tensor. This is the Levi-Civita curvature. And EI is just some orthonormal basis. Okay. And then in any case, we call this, this is the Ricci form, which has these various well-known properties. So D rho is 0, and it's a 1-1 tensor. So this is all in the Kähler setting. I'm working completely here. Okay. And so we can define Kähler-Ricci flow in terms of the Kähler form as follows. So given M2nj, a family omega t of Kähler forms solves Kähler-Ricci flow if we have the following equation. So del omega del t is minus rho. Okay. So we flow the Kähler form by the negative of the Ricci form. Okay. And just recall some very basic facts. So first is this admits, there are several ways to prove this, but this admits short time solutions. And in a sense, there's something non-trivial here to show that this is preserving the Kähler condition. These two facts are kind of related. Also, this preserves the Kähler condition. It's sort of trivial the way that I wrote it, because I already said it was a one parameter family of Kähler metrics. But in any case, third is the family of associated Riemannian metrics satisfies just the usual Ricci flow. So dg dt, I guess the way I've set it up is just minus Ricci g. So there's this difference of a factor of 2, but this is not so important. You can just scale at time and it's okay.
Can I ask a question about this short time existence?
Uh-huh.
So is it possible to prove this rigorously using things like Banach manifolds and thinking of it as like an ODE in infinite dimensions?
Well, in a certain sense, all the parabolic regularity theory, like at the very bottom level, does come down to this, or is more or less thought of this way. Yeah. Thinking of the evolution problem as an infinite dimensional ODE. Yeah, usually at the lowest layer of the analysis, that's what it comes down to. Yeah.
And where does ellipticity come in?
Basically, in showing that that like the linearized problem acts sort of like as a contraction mapping on a space like that. That's usually the ellipticity condition. Yeah.
And so what is the main technology for these short time existence results?
So you mean the main technology for establishing like short time existence of parabolic equations on compact manifolds?
Because I know that it's very different from the type of technology that's used to for example, to show existence of like Ricci flat metrics or something like that.
Right. Well, Well, okay, I guess maybe there's two answers. One thing is that those two things you say are, of course, very closely related. I mean, to get into the detailed analysis of Kähler-Ricci flow, it's very similar. I mean, in fact, I'm going to discuss one of the main results, one of the main kind of basic results in Kähler-Ricci flow theory, which gives a different proof of Calabi-Yau theorem. And it's very much, well, okay, I said it's a different proof, and it is a different proof, but it's very, very similar to Yau's original proof by the elliptic method. I mean, there's definitely a similarity in the type of analysis, but this sort of short time behavior of Kähler-Ricci flow is sort of a very general thing, and it doesn't take you very far to say it has short time solutions. I don't mean that like in the sense of time. I just mean in the sense of actually proving something. I mean, this general theory tells you, give me some metric, and there is an epsilon such that I have a solution for time epsilon.
Okay, last question about this thing. Isn't it local? I mean, why is short time existence a global problem?
Global on M, you mean?
Yeah.
Well, I guess there are different questions one could ask, but you know, I mean, typically for a parabolic or an elliptic equation, you're solving in some sense a boundary value problem, right? So when you're solving an elliptic
boundary
conditions, so when you solve an elliptic equation on a compact manifold, well, you don't have any boundary conditions.
Mm-hmm.
When you solve a parabolic problem on a compact manifold, you do have a boundary condition, right? It's the initial time slice is your
yes.
So but of course, with many of these equations, I mean, Ricci flow in general included, one could imagine asking to solve it on like manifolds with boundary. But the thing is, even for Ricci flow, like non-Kähler-Ricci flow, just general Ricci flow, I mean, there has been work. I forget. I don't think I could really say exactly.
I guess what I'm asking is, if you could show that there's short time existence on any open set, and if you could show that it's unique, then that would be enough, right? You could just prove it for the whole compact manifold. Because then, you know, there would be a short time existence on every open set, and then you take the minimum of whatever those short times are.
Oh, well, yeah, but I think that if you want to think that way, so if I'm understanding correctly, or maybe I just make a new.
But there is no uniqueness on small open sets, right? So this is the problem, really.
It's not like Cauchy-Kovalevsky, actually. It's because you have
like
less derivative in T.
Yeah, if you want to localize in space, you would need to prescribe the boundary condition like on a cylinder going forward in time. And that's what you don't know. That. Although, having said that, you can make a little, in some sense, people do argue the way you say, but you have to use cutoff functions.
Mm-hmm.
And it's more trouble than it's worth maybe for compact manifolds, because you can just quote the theory for compact manifolds, but people do what you're saying when they want to understand the flow on complete manifolds. So to claim short time existence for Ricci flow, for instance, on complete manifolds, at least the initial, and maybe you assume some nice initial data like the curvature is bounded, then people basically do, in a sense, what you say. You get these local solutions by using a cutoff function, and then they patch them together. They prove a lower bound. So there, right? You can't just appeal to some finiteness of the cover. You have to prove a lower bound for the existence time. But
maybe I was completely wrong in saying that it's a local problem. I mean, maybe short time existence near one point. No, you know, it needs to use the metric on the entire manifold.
Well,
I mean, if you said that it's not unique, right? You cannot tell the future behavior of the metric in an open set without prescribing some kind of boundary data
right.
going forward in time, right? So it's
I guess, yeah, if you want to think of it that way, it is sort of inherently, I guess, a bit global, yeah. And yeah, these proofs that I mentioned of like arguing on complete manifolds where you sort of patch together, in a sense, the whole point is to sort of well, I don't know, I guess like control the influence of far out regions, I guess you could say. It's not, it doesn't really manifest that way in the proof, but that's, I guess you could say that's what's going on.
Okay, sorry about that.
No, that's good. Okay, so yeah, so I guess maybe I wrote these things a little bit out of order in a sense. So if I have this solution as stated, I already assumed it's a family of Kähler forms. But alternatively, what you could think of this as is just saying the Ricci flow equation, starting with a Kähler initial condition, will preserve Kähler, and the Kähler forms will satisfy this equation. Okay. And of course, yeah, of course, Ricci flow sits inside generalized Ricci flow, right? As the case h equals 0. So in a sort of tautological sense, we've found already an interaction between like generalized Ricci flow and complex geometry. Okay, so what sort of theorems do people try to prove with this? I just want to sort of mention a few key results. So first is you can give a complete proof of uniformization of Riemann surfaces. So so given M2J, a compact Riemann surface without boundary. Anyways, everything for us is without boundary. And any G naught Hermitian metric on MJ, which is of course automatically Kähler. The solution to Kähler-Ricci flow suitably normalized exists on an infinite time interval, half infinite, so exists for all forward time and converges to a constant scalar curvature metric. Okay. So this type of result is the sort of well, it's sort of the gold standard for what you might try to prove with these things. So you have, you know, any underlying topology and any initial data, and you get global existence. And I'm leaving off what this normalized part means. You have to sort of, well, scale the metric according to time in a certain way, but this is not so important. So it exists for an infinite time interval, and then moreover converges to some known quantity, converges to something rigid, a constant scalar curvature metric. And just as a remark, it's fairly well known, but not completely well known. So this is sort of originally due to Hamilton and Chow, although the proof of or let me say it differently. So the a priori proof of uniformization came much later. So all I mean is that their original proof was a theorem about the flow, assuming one already knew the existence of a constant scalar curvature metric on the given Riemann surface. But in any case, in the end, it is possible to prove what is claimed about the flow without using that, and thus you indeed get an a priori proof of uniformization out of Kähler-Ricci flow.
In the end, the a priori proof, is it simpler or much harder than just
It's
using the
not
continuity
that
method?
much harder. Yeah. This is this very short paper. It's I forget the authors. Sorry. It's a very short paper. It's Lu Tian. I think it's a very short paper. I can maybe give the precise reference later. It's a short paper which just sort of clarifies what had been done up to that point and just where in the proof uniformization was used. And it's just a few extra arguments to make it completely a priori. Basically, they use, well, the key point is to sort of classify solitons and show that there aren't any compact solitons that they have to, that basically the only real issue is that on S2, you need to make sure that you converge to a round metric and not some solitons. You just show that solitons do not exist on S2. And this is, it's a short, like pretty classic argument. Yeah, so this is a classic thing. And then another sort of very basic, oh, sorry, I don't mean basic, I mean fundamental, a result about Kähler-Ricci flow is a new proof of Calabi-Yau theorem. I mean, this was essentially the first thing that was proved about Kähler-Ricci flow. Okay, so again, let me just state it as a Kähler-Ricci flow theorem. So this is due to Tsao. So you're given M2NJ, a Kähler manifold C1 is 0. And then given G0 Kähler, the solution to Kähler-Ricci flow with this initial data exists on an infinite time interval. Here, there's no normalization issue. And converges to a Ricci flat limit on G infinity. Okay. So again, it's sort of the strongest possible result one could hope for a problem like this. You give me a certain topology, in this case, trivial first Chern class, and you give me any initial data valid for the problem, and you get the optimal existence, which is infinite, and then moreover convergence to a strong limit. And so in particular, this is, I mean, even more is, he proves more than this even in his paper. Like there's other cases that are handled, but I just want to focus on this one. And so in particular, as a corollary is the Calabi-Yau theorem. So in particular, right, in any Kähler class, so you fix any Kähler class, then you just take any initial data and you'll flow to something canonical, to Ricci flat. Okay. So yeah, I'm actually going to basically give a proof of this theorem eventually. But yeah,
Jeff,
so
is it known what happens on Fano manifolds which are not k-stable? Where does the flow converge? Or
yeah, so that's very much an active question still. there are results showing convergence to a soliton. I forget the precise formulation, but I think in some cases you expect convergence to a soliton, and that can be shown to happen. But it's still a very delicate question. Yeah. So yeah, so in view of these results, I mean, some very broad goals. That I'm going to sort of refer back to. One is to sort of uniformize, classify complex manifolds in higher dimensions. And two, we could sort of ask to maybe generalize the Calabi-Yau theorem into, well, more broadly into Hermitian geometry, but maybe let's specifically say into generalized scalar geometry. Okay, this is something we might want to do. And so, yeah, and then maybe here specifically, at least the case n equals 2, we might want to complex dimension 2. And so, yeah, so it was sort of with these very broad goals in mind that we set out initially a long time ago to try to define versions of Ricci flow that had something to do with Hermitian geometry outside of the Kähler context. And I'm going to sort of discuss it a bit from this more classical point of view, but I sort of very quickly want to try to connect to the generalized Ricci flow point of view. Okay. So yeah, so any more questions before? So yeah, I'm going to say some words defining now this pluriclosed flow. Okay. So let's start with a definition. So given M2Nj, now just a complex manifold. A Hermitian metric G is pluriclosed, also known as this like strong Kähler with torsion, SKT. If omega, which again is GJ, satisfies DDC omega equals 0. So this is the same as I del bar omega equals 0. And then maybe looking forward, we could maybe say H is DC omega and DH is 0. Okay. Okay, so why do I define this? So I mean, again, just thinking very broadly, if I do want to try to prove some kind of uniformizing or find some canonical metrics or something on higher dimensional manifolds, they're not all going to be automatically Kähler. These manifolds don't have to admit Kähler structures, so I somehow need to allow for a more flexible geometry, and this is a more flexible sort of geometric structure which has Kähler metrics as a special case. And just a starting remark, I just mentioned this result, this key result of Godeshan. So given M2nj G Hermitian, there exists a unique smooth function such that I have to normalize. So the integral over m of u dv is 0. That's 1. And second is I del bar of e to the u omega to the n minus 1 is 0. Okay. So what this is saying is, well, this condition is now called, this condition is now usually called Gödelschaft. But of course, when n equals 1, this is saying that the conformally related metric is pluriclosed. Okay. So sorry, this is the Gödelschaft condition for the metric e to the u g, or the Kähler form e to the u omega. Okay. And when n equals 1, that condition is the same as pluriclosed. So it's saying you can sort of impose this scalar function. So this is an equation of top degree forms, right? So you can impose this kind of scalar equation always on a Hermitian metric by a conformal change. Okay. Sorry, not 1. Sorry, n equals 2. Okay. So yeah, and then in the case of complex surfaces, you always, so you can always take any Hermitian metric and then conformally modify, and you get something that satisfies this pluriclosed condition. Okay.
Is it known any construction of pluriclosed metrics, like a very general construction of pluriclosed metrics in complex dimension 3?
I don't think so, actually. Maybe.
I mean, beyond homogeneous manifolds.
No, that's a good question. Yeah, so maybe I just emphasize that. Yeah, I think that's a good question. Like for instance, there, well, I guess by now there are some structural tools, right? So I guess Anna proved that like blowups of SKT are SKT, right? There are some general tools like this, but what would actually be nice would be maybe something like a Nakai-Moishizan criterion. So if you have some sort of cohomological data satisfied, then you can find a pluriclosed metric in some Epley class or something like this.
Well, there is a characterization in terms of Harvey-Lawson type in terms of currents.
Right.
Pretty much like in the Kähler case, but actual
Right.
is more complicated.
That's right. Yeah. Okay, so yeah, so I'm gonna define this pluriclosed flow equation, which is an equation for pluriclosed metrics, but I just recall some further basic geometric definitions. So if I have M2nj a complex and G Hermitian, sorry, let me try to get the constants right, although it doesn't maybe matter so much. So the point is, it doesn't really help us at the outset to use the Levi-Civita connection, because this is not Hermitian anymore. But since we're also not in the Kähler setting, we don't have, well, there's more than one Hermitian connection around. And so we'll end up kind of using both. So first we have the churn connection, which I'll denote like this. So nabla x, y, z. So the churn connection. This is the Levi-Civita connection minus 1/2 d omega jx y z. And then we have this bismuth connection. So this differs from the Levi-Civita connection by by minus 1/2 dc omega x y z. Okay. So I've expressed these as connections on the tangent bundle. The key point is that they're both metric compatible and preserve the complex structure as well. But of course, as we're in this sort of, in principle, torsionful setting, they're not torsion free. Okay. And they're not the Levi-Civita connection. Okay. And also, as I said, these are not the only possible Hermitian connections, but you could actually take the two of these, basically span a line, which is this sort of canonical line of Godeshan connections. But these are the only two that will be relevant to us. Okay, and so using these, we further define so RBC, B or C, will be the curvature tensors of these connections, respectively. And then we'll also get these Ricci forms, so rho BC. And these are defined exactly as I defined the Ricci form in Kähler geometry above, just using the curvatures of these connections. So X, Y, J, E, I, E, I. Okay. Whereas before, E, I is just some orthonormal basis. Okay. And you can, of course, also interpret these as the curvature of some induced connection on the canonical line bundle, if you like. Okay, so this is bismuth or churn Ricci forms. Okay. Okay, and just by general theory, one can prove a few basic facts. So one important part is that these are still closed. This is still just sort of the Bianchi identity. These are still closed, but a sort of subtle but important fact is that is the type consideration. So the churn Ricci is of type 1-1, but the bismuth Ricci, well, I mean, of course it can be, but it is not. So maybe just to emphasize, it's just not always 1-1. Okay. So it won't necessarily be of type 1-1. Okay, so so with these around, with these curvature objects around, I can at least abstractly give the definition of pluriclosed flow. So so given M2M J, a complex manifold. So a one parameter family omega T of pluriclosed, let me just call it a metric, satisfies a pluriclosed flow if del omega del T is minus rho bismuth, but then I project to the 1-1 piece. Okay. And yeah, so let's just start with a few basic remarks. So why, well, I maybe will spare, it's maybe not so important exactly how we guessed this. We didn't exactly even guess it in this form. But you can at least perhaps believe, so since rho bismuth is closed, this implies at least that DDC of rho bismuth 1-1 is 0. So that follows easily. And so at least the equation appears to be well posed. Second, well, this does admit short time solutions. And sort of, I guess, importantly, so the linearization of minus rho bismuth 1-1 at a so the linearization, excuse me, of this operator at some metric G, say in the direction of H, is G J bar I del squared H K L bar by del Z I del Z bar J plus some lower order terms. So the point is, if I think of this Bismuth-Ricci curvature, the 1-1 piece, as a differential operator on the space of pluriclosed metrics, then its linearization is somehow the simplest possible one. Sorry, I just make up some notation. I mean the linearization of this operator at a metric G in the direction of H. I make up some notation for this. And you get the simplest possible sort of symbol related to a metric G.
You mean this is an operator that takes a metric and computes this?
Yeah, like a map from like 1-1 tensors to 1-1 tensors that takes a metric to the Bismuth 1-1. Yeah.
And this is like G times H or something.
Sorry, can you repeat that?
And this is the expression that you wrote out as like the first part in the Taylor expansion of G plus TH or something.
Yeah. Yeah. Yeah, exactly. Yeah, and we'll come back to sort of maybe like a rigorous proof of short time existence, but there's different ways to do it, I guess. And third, well, again, with hindsight, this all seems very sort of, I guess, simple, I guess, but somehow this projection to 1-1 I mean, again, we didn't originally find it in this form, but it might seem odd, like what's happening to the 2-0 piece? And it turns out, of course, that you want to, it turns out to be helpful to include something which keeps track of the 2-0 piece. So, the following equation. So del beta del t is minus rho bismuth 2-0. So here, beta t is a family of 2-0 forms. And these will have the relationship. So again, maybe just to emphasize, we sort of originally discovered this pluriclosed flow sort of in this form. And of course, it does contain all the information you could say. I mean, the Hermitian metric, that's it. And it'll give you the torsion, it gives you everything. But somehow keeping track of this torsion potential along the flow is very helpful in various settings. So these will preserve the condition that del bar beta, sorry, del omega 0 plus del bar beta t is del omega t, I guess. Yeah, so this is like if we think of del omega t, I mean, this is a crucial sort of new feature along the flow, right? We have this like first order invariant, this thing that you don't really have in the Kähler setting. And somehow having this kind of holomorphic potential for it is extremely useful in the analysis. Okay, so in the book, if you look, we sort of include both of these as sort of the definition of pluriclosed flow. Even though in the strictest sense, you only need the first one. Okay, and so before moving on, I just want to.
What does the box equation mean?
Sorry, yeah, this holds for all time. You can just easily check, assuming I got the signs right, that you can just like differentiate both sides, and using that d rho is 0, you see that that this is preserved. That it's tautologically true. So maybe I add an initial condition, beta 0 equals 0. So it's tautologically true at time 0, and you differentiate, it's true for all times. And so it's well, and yeah, this is an equation, right, of 2-1 forms. And like I said, it's sort of, in the strictest sense of like describing the time t geometry, it's not, I guess, necessary. But all the analysis that I can do for this involves this beta somehow. Somehow it's extremely helpful to keep track of this beta. Does it, I don't know, does it help or? Okay, so yeah, I just want to, well, ask in a, maybe I erased this. So ask in a very broad way. How does this pluriclosed flow equation interact with generalized geometry? And, we do have, I'm going to show some answers to this. And again, maybe I just sort of emphasize, like as a advertisement for generalized geometry, that basically all the actual analysis you can do uses the language and structures of generalized geometry. Somehow, if I never looked at those papers, I never would have proved anything about this equation. So somehow almost all the hard analysis in some sense relies on structures from generalized geometry. And I'm going to explicitly explain, or well, eventually I'll describe some interaction, I guess, between them that helps in the analysis. But I mean, again, as I understand it, and maybe Marco or somebody can say something, but that this sort of SKT geometry maybe sits inside generalized geometry in more than one way, kind of, or that there's sort of different ways of thinking of how SKT fits into the language of generalized geometry. And so we've sort of found a few successful ways to, well, a few successful points of contact, but maybe there's more. I don't know. But so yeah, okay. So, but so this is the equation. So written so far as an equation of Kähler forms. But so far, according to the story, you know, I've just kind of taken us on a tangent. This was supposed to be about generalized Ricci flow. Okay, so let's see how that works. So what does this have to do with generalized Ricci flow in the first place? Okay. So I'm going to explain this result. So given M2N J and G some Hermitian metric, the Lie form is as follows. So by our convention, the Lie form is theta. This is minus d star omega composed with J. Okay. So different conventions, I'm sure, exist. But for us, this is the Lie form, which is a one form kind of measuring the non-Kählerness, if you like. And then we have the following theorem. I've not been maybe very careful about accrediting, but this is from this earlier work with Tian. So given M2N J and omega T, a solution to a pluriclosed flow, the associated pairs, so I expressed it as a flow of Kähler forms, but the associated pairs of metrics and HT, and yeah, maybe for emphasis here, this HT, I mean DC omega T. So these associated pairs satisfy the following equation. So del G del T is minus Ricci plus 1/4 H squared. I forget the sign. So minus the Lie derivative with respect to the Lie vector field of G, and del H del T is a minus d star with respect to G of H minus the interior product of theta sharp with H. Sorry, I wrote something stupid. Minus the Lie derivative with respect to theta sharp of H. Okay. Maybe I can, I don't know, check the sign. I think it's minus. So yeah, so what is this saying? So this is just a, what is this? This is like a canonically gauge fixed generalized Ricci flow. Okay. So in general, one can take, you know, so I think we discussed, you can take any solution to generalized Ricci flow. Of course, you can pull it back by some time-dependent family of diffeomorphisms and get a gauge equivalent flow. But somehow the pluriclosed flow kind of comes to us comes to us, well, in the form of generalized Ricci flow, but gauge fixed by this Lie form. Okay. And this is a sort of a key feature. Okay. And maybe just as a remark, so putting everything back to the regular generalized Ricci flow gauge. I mean, I just want to be precise about this point. It's not correct to say exactly that generalized Ricci flow preserves pluriclosed. I mean, it's sort of correct, but I just want to really emphasize this point for later. So what does it mean? So if I start with a pluriclosed metric and I run generalized Ricci flow, it sort of will correspond to a pluriclosed structure, but only after I also evolve J, right? So maybe I just emphasize dg dt is minus Ricci plus 1/4 h squared. Dh dt is minus dd star gh. But then del j del t will be the Lie derivative with respect to theta of j. So I've kind of removed the gauge term on g and h at the expense of inserting a gauge term for the flow of j. And a sort of surprising or not, depending on your point of view, fact is that this is also, in a sense, a heat equation. So this is the G tensor Laplacian of J plus some fairly nasty algebraic term. So the Riemannian curvature acting on H, and then plus like an H squared type term. Okay. And just again, as a sort of broad question, how I don't really know. Well, I don't really know like a good way to actually sort of use this equation. Although in a sense, the generalized Kähler-Ricci flow to come, in a sense, is entirely based on analyzing this equation. But in general, it's hard to really see much meaning in these lower order terms or to get some sort of analytic structure out of them. So it would be interesting if somehow there were I don't know, a sharper form of this equation which allowed one to use it in a broader way. Okay, but just the point is, if I'm solving generalized Ricci flow with a pluriclosed initial condition, that will correspond to a pluriclosed metric as long as I use the time-dependent complex structure. Okay. I think it's a little bit strange. We usually would think of these complex structures as sort of rigid objects, and in a sense, my flow is trivial. It's by diffeomorphisms, but viewed a different way, it is a heat equation as well. So there's some subtlety there. Okay, so maybe that's the first remark. And then I guess the second is, since we've now shown the way, well, shown that this pluriclosed flow is generalized Ricci flow in disguise, we immediately obtain a gradient interpretation for pluriclosed flow. This is this F functional which I think both Mario and I discussed before, as well as entropies. Okay, so we discussed a little bit these W plus minus functionals. Okay. Okay, so yeah, I'm not really gonna, I guess, sort of review these, but the point is those functionals are diffeomorphism invariant, and so all these monotonicity properties and these gradient properties sort of immediately follow for pluriclosed flow, since it's just a gauge fixed version of generalized Ricci flow. And as a sort of open question related to this, could ask what what special features does, for instance, this F functional have in this sort of pluriclosed setting? For instance, you could consider you could sort of implicitly think of it as a functional defined on sort of all possible pluriclosed structures, and you could consider varying with respect to J, for instance. Or try to also understand the second variation for pluriclosed metrics. So there's some sort of general, I guess, well, there's some general computations of the second variation of this F, but presumably they're much more special in the pluriclosed setting or the generalized Kähler setting. I think is possibly an interesting thing.
Can I ask a question?
Yeah, sure.
Is the generalized Ricci flow, that's defined for any Riemannian metric with a closed 3 form?
Uh-huh.
So it doesn't require like the complex structure. It's like a
right.
Let's see. And
yeah, that's kind of the point I was trying to say. So it's kind of like this. So the story of Ricci flow, right? You have this Ricci flow equation, which doesn't need a complex structure, but then somehow when you add one and add the Kähler condition, you get a fruitful interaction between them. Or in any case, all that structure is preserved. And so it's kind of the same story here. You have this generalized Ricci flow equation, which only needs G and H. But when you add the right sort of cocktail of conditions from complex geometry, like a complex structure and a pluriclosed metric, then all of a sudden it seems to preserve that. But again, in this sort of slightly more subtle sense where the J has to change as well.
What's the kind of the history of how the generalized Ricci flow was discovered versus the pluriclosed?
Well, I can give you my point of view. I mean, I think, well, I mean, I think as far as the math literature is concerned, there were a couple papers. So there were some papers by math physicists right after, well, pretty soon after Perelman's work. So maybe I can write something. Well, maybe I just talk. It's okay. So this is this paper of Oleinik, Sunita, and Wolgar. It's referenced in our book, and they basically extended. It's a relatively straightforward thing once you know Perelman's F functional to include this H. And they're coming purely from the physics point of view. It's all studying renormalization group flow. And then I also wrote some papers on some very basic things like that I discussed last year, like the regularity and compactness stuff. Not really thinking of it as generalized Ricci flow, just thinking of it as like Ricci flow of connections with torsion, even though it's the same equation. And then later, we said, well, okay, how about we find some, so when I started to work with Tian, we say, oh, how about we find some places where torsion arises quite naturally, so like complex non-Kähler geometry. And then we sort of wrote this big class of equations in Hermitian geometry. And then it turned out that sort of the most interesting one, or at least, well, maybe I back off. At least at that time, the most interesting one was this pluriclose. We sort of found that then separately. And then after that, realized that it sort of was just this generalized Ricci flow in disguise. Somehow, I don't know, looking back, it seems like I should have discovered all of this in the course of 1 week, but instead it took several years. But I don't know, because in the end, it's just some sort of clever curvature identities to sort of relate all these different flows, but it's sort of coming from different points of view somehow. But yeah. So yeah, so I guess the pluriclose was discovered purely by just saying, well, we just want to try to do some uniformizing flow in complex geometry. And then a little bit later, we discovered, okay, so it is this flow, it's this natural kind of RG flow of metric with 3 form. And then we only later called it generalized Ricci flow, really, after realizing that whole story connected to generalized geometry. Okay, so yeah, and then, well, so further, yeah, building on this connection to generalized Ricci flow, we sort of immediately obtain this sort of regularity requirement. So we discussed this theorem, but so this basically says if the solution exists maximally on some time interval of this form where t is less than infinity, then the limit as t goes to capital T of anyways, it don't have to be so precise, I guess, but lim sup as t goes to capital T of the C0 norm of the curvature is infinite. So the curvature has to blow up at a singularity, and so we don't have to prove anything further. This immediately follows just from the fact that it's generalized Ricci flow in disguise. Okay. But of course, yeah, so the whole point of maybe moving into the setting of complex geometry is that we want to do better than something like this. We want to prove much sharper results than this. Like, for instance, these theorems I mentioned earlier. So, and so, yeah, I guess my plan at this point was, so in view of this regularity requirement and the idea that one expects to do much better in complex geometry, I was going to go back and prove this theorem of Tsao. So I don't know, maybe, are there any further questions before I sort of switch gears? Okay,
Yeah,
so
I have one question.
Yeah.
So I'm just wondering about whether you have a better understanding, kind of qualitatively, what if we just think, let's say, of the generalized, what do they call it? Where you only have one half of the structure. So hyperkähler, Kähler with torsion. Suppose you have strong Kähler with torsion and you implement this flow. So is there some, what's the qualitative picture? What's the analogy, let's say, to usual Kähler Ricci flow in terms of the, moving to the boundary of the Kähler cone and so on?
Yeah, so, well, this is all to come. I'd hope to, but you know what, maybe it's actually better to, I tell you what, yeah, maybe, because I don't want to run too late. This South theorem maybe will take a while. Maybe I'll start with that next time and instead answer your question.
As you like.
So yeah, maybe I just, so this curvature blow up thing is it's a very general result. So let's instead maybe answer Marco's question. So what can we expect for this, for pluriclose flow? Expect / hope, I suppose, for pluriclose flow. And to start, I'll recall this key result of Tianzheng, which is what you said, but I'll just recall it anyways. So you have n to n, J, this is compact Kähler manifold. And so we'll say K is the Kähler cone. So this is the set of classes phi in the 1-1, like a Dolbeau cohomology, such that there exists a Kähler metric omega in the class. So this is the Kähler cone. And so associated to the Kähler cone, or sorry, what I mean is given, so omega t, a solution to, sorry, I'm in the Kähler world. So a solution to Kähler-Ricci flow, you immediately get sort of like an ODE in this finite dimensional space. So omega t as a class, well, this is the class of omega naught minus t times, well, the whole point of, the Ricci form will represent the first Chern class. Again, maybe I'm sloppy about multiples. Use some 4 pi or something. So you just, because the Ricci form represents the first Chern class, the cohomology class moves in this way. So this is just omega 0 minus TC1, okay? I guess the way I wrote it, C1 is like my notation is not good, but I think it's clear nonetheless. So, yeah, so we have this Kähler cone. So you have every Kähler metric defines a class in H11, and it happens to be positive. But then on the other hand, this class is moving along the flow. And so certainly immediately you get an upper bound for the existence time that has nothing to do with really anything analytic. You define tau star is the supremum of times t greater than 0. Sorry, let me write it differently. Supremum of the set of times t bigger than 0, such that omega naught minus TC1 lies in the Kähler cone. And yeah, this is depending. This is T star of omega naught. Okay, so you give me an initial metric. I get some time, tau star omega naught, which is sort of the largest possible time it can exist. Because once the class isn't a Kähler class, something must have gone wrong with my PDE. Or at least as a smooth metric, I can't possibly be, I can't exist at this time tau star. So that's just a simple remark, which I can just summarize as saying, if capital T is the maximal existence time, it will be less than or equal to tau star omega naught. Or in other words, the flow has to at least go singular by time tau star omega naught, right? So is this okay? And then basically the result. So this is the theorem of Tianzheng. So the actual theorem can now just be stated as T equals tau star omega naught. So this is the heart of the result. So in other words, until my class leaves the boundary, leaves the Kähler cone, I will exist smoothly. Okay. So, and again, maybe just for emphasis, this T is the maximal, maybe emphasize smooth existence time. Okay. And so, yeah, in a certain sense, after this theorem of Tsao, and sort of which itself is kind of building on all these Calabi-Yau theorem estimates, this theorem is not such a big leap upon that. But then, of course, all the subtlety then becomes, well, what's happening at time tau star? And this is where all the topology enters, blow-ups, blow-downs, not blow-ups, blow-downs, flips, and all these other behavior that's still, well, it's still largely poorly understood, I would say. But there are many, many partial results in different settings. But so, yeah, so basically based on this, we made an analogous conjecture. So this is a very clean result, right? Which tells you sort of purely in terms of topology, especially once you have this sort of Moishezon criterion for K, basically purely in terms of topology, you know how long your flow will exist, right? This is way stronger than what exists in like the general Ricci flow setting. Yeah, but so based on this, we made a similar conjecture. So I have to recall some definitions. So M2NJ is some complex manifold. Then I'll define this special Epley cohomology space. So this is the kernel. This is the kernel of DD bar as a map from real 1-1 tensors to real 2-2 tensors. So I DD bar. Modulo a certain image, and so that image is the sort of natural embedding of a 1-0 form. So this is modulo del bar alpha plus del alpha bar, where alpha is a 1-0 form. Okay. So this is the 1-1 Epley.
Jeff,
Yeah.
I'm a bit confused by the theorem you stated and the result you stated for Riemann surfaces. So for the Riemann surface case, you said that the flow exists for all time.
Yeah, I sort of cheated. I said after normalizing.
Okay.
Where did I write it? So here, yeah.
Okay, you normalize by t minus tau.
Because yeah, so on the sphere, of course, there's a finite existence time, but then once you consider this normalized flow, you stay fixed in cohomology the whole time. So, yeah. So yeah, so this is this Epley cohomology, and then inside this, so every pluriclosed metric, of course, defines an element in this cohomology space, and then I can define what I think we usually call P, which is the positive cone. So this is the set of classes B in H11A such that there exists a pluriclosed metric omega in the class. Okay. So positive cone. Okay. And then, yeah, so after this, the guess or the conjecture is in direct analogy. So given omega naught pluriclosed, or sorry, let me just say it different. So given omega t a pluriclosed flow, we get this exact same equation. Well, maybe I just sort of do the trivial computation. So I can take the time derivative of this class, and this is just, well, the point is that the 1 part of the Bismuth tensor, of the Bismuth Ricci tensor, will define it defines a pluriclosed 1-1 form, and sort of suitably interpreted, it still represents the first Chern class. Okay, so it's the 1-1 part of a form that represents the first Chern class. So in a sense, this is still a minus C1. And so as an equation in P, you get that omega t is omega naught minus t C1. Okay. So I guess the thing to check is that so you can take like a usual representative of C1, say with respect to some Chern connection, that will be a closed 1-1 form. And then in the usual sense, that defines a class which you can interpret as a class in H11. And then you just have to check that the Bismuth Ricci 1-1, sort of allowing for this more general space in the denominator, is a representative of that same class. So it's just the usual first Chern class, but sort of interpreted in Epley cohomology. Okay. So yeah, so the point is we do move in this cone, and then tau star of omega naught by definition is the same as it was above. So this is the largest time such that omega naught minus TC1 lies in the positive cone. Okay. And then the conjecture and this was how we set things up in this original work with Tian, is that the solution to pluriclosed flow with initial data omega naught exists smoothly on 0 tau star omega naught. Okay.
So if you have a Keller background, is it still a conjecture, or it's?
Unfortunately, yes. Yeah. So there's lots of cases. I mean, it's still a conjecture because it certainly has not been disproved. But then there's many cases where it can be confirmed. But yeah. So having a Keller background, it does help the analysis in many respects, but not enough to get it all the way.
So what are the cases where you know this is true?
Well, I'm going to discuss some of those. I guess, yeah, maybe as a preview for next time, I'll discuss one of the main theorems I want to discuss is if you have T2N, J complex torus, and this is of course very special, then, well, and let's say you have omega naught pluriclosed, then the solution to pluriclosed flow with initial data omega naught. So it's a torus, right? So C1 is 0. So the tau star is infinity, right? So you expect it to exist for all time. So And that's true, and it converges exponentially to a flat Kähler metric. Okay. So I suppose next week, or in any case, eventually, I hope to get to this and prove this theorem. And it's kind of, well, I think that this theorem is sort of why one should believe the conjecture, kind of. I mean, like for what's the point? Like for regular, like non-Kähler Ricci flow, you know, you can do these like neck pinch singularities on any manifold, any topology, right? Like the singularities don't have to have any topological significance. And if something like this was possible for pluriclosed flow, you would see it. You could do that somehow on the torus, right? So this is somehow suggesting that there is like a rigidity phenomenon, and that there
But
should be
what-
some kind of like complex topological significance to the singularities. And
What's
I guess
the
another
three form in
kind of-
that case?
say that again.
What's the three form in this theorem?
So the three form is always so HT is always DC omega T. And so in particular, H goes to 0 exponentially.
So H is, so in this, for your initial pluriclosed omega naught, that three form could be non-trivial in cohomology.
Well, no, it can't. I mean, it's basically because of DD bar lemma, I guess. It
Yeah.
will not be.
Okay.
It will
I
not
see.
be. Yeah. And that's important again to the way the analysis works. Yeah, somehow the non-triviality, the sort of cohomological non-triviality of torsion is a very delicate point in the analysis, and sort of rears its head in funny ways.
But in the conjecture, there's no mention of the three form or the cohomology
Well, I don't
class?
need to. It's implicit. So H in particular, this will go to 0 exponentially. That's, I mean, this fact I said about it being cohomologically trivial, that just follows from the fact that torus has DD bar lemma.
Okay, but in general, in the conjecture, you're expecting H to become harmonic, I guess.
Oh, well, I mean, yeah. So maybe just to emphasize, let me just go back up to the Tianjin theorem. So they claim, you know, I didn't write it precisely, but they prove that like the Kähler Ricci flow exists smoothly up to when you hit the boundary of the Kähler cone.
Mhm.
But all kinds of stuff can happen there. I mean, it's very delicate.
Sorry, maybe what I'm asking is something very naive, that if you do pluriclosed flow in a case where the cohomology class of the three form is non-zero, then that has no impact on the conjecture statement. I mean, you're just expecting H to go to the harmonic representative somehow of the eventual metric.
Well, that is the most naive guess, which I guess, so probably, I guess you can, I mean, you could prove if you're in a situation where the existence time is infinite, and moreover, the solution is non-singular, even then you can't really prove that, but it's not true because there can be some collapsing. But I guess if you assume that there's like a smooth limit at infinity, then at least you get this sort of soliton version of harmonicity. You get D star H is grad F of Cook H or something like that. That follows from these Perelman functionals.
But somehow the cohomology class of H does not. How does it relate to the Epley 1-1 cohomology? Is there an interaction between the H11 and the three form class?
Well, okay, yeah. Let me make maybe a few remarks about that. So for one, yeah, I suppose I should have said this sooner. So yeah, so HT is DC omega T, and that class is preserved. That's a very general fact. That's true, like just for generalized Ricci flow. That class is preserved. And yeah, the most, in the simplest kinds of limits, then yes, it's reasonable to expect that HT limits to the harmonic representative with respect to the limiting metric. Yeah. That's sort of the, yeah, that is the correct, most simplest expectation. And yeah, maybe I just mention, since you asked, like a case where you do see that. In fact, I proved this in my recent paper. I can talk about this. So just like the generalized Ricci flow with an S1 invariance on S3. So like you think of the hop vibration over S2, you start with certain symmetric initial data. You get that it exists globally and converges to this sort of canonical Bismuth flat structure. So it's the round metric with H is, let me just punt on there's some constant factor, but it's basically a multiple of the volume form of S3. And so this is like the first case where you can really see like the sort of, yeah, like the topology of the torsion, the cohomology of the cohomology class associated with the torsion having like a real qualitative effect on the flow. So if you start, of course, like if the bundle was trivial, well, so the topology of the bundle here is related to the cohomology class of H with this S1 invariance. But so if instead you just look at like S2 cross S1 and think of just like G and then H is 0, then it's just Ricci flow on S2. And as Mario mentioned, it has a finite time singularity. Which again, just to clarify, like this thing I said earlier, you have to like normalize the flow to get the convergence. But so yeah, so the topology definitely has, or this cohomology class of the torsion, I think is a really crucial thing about the flow, and you can see like in this simple example how it has like a strong qualitative effect on what you might expect. It takes a situation where one has like a finite time singularity, like Ricci flow on S2, and produces something with a nice long time solution and convergence to a nice structure.
I have a question actually. Suppose that this tau star is infinity. What kind of convergence do you expect in general? Is this?
Well, yeah. I mean, the thing is, even with tau star infinity, like, I mean, like even in the Kähler-Ricci flow setting, you can have like collapsing at infinity. This is probably the main thing, but there's even examples now, I guess, of infinite time curvature blow up singularities, curvature singularities that take an infinite amount of time to form. Unfortunately, it's still quite difficult, even with the long time existence. I guess the collapsing issue is maybe the main difficulty, but there are others as well. But I guess assuming infinite existence time and some geometric control, then you can get something more like what you might expect. So then these sort of monotone functionals will tell you get convergence to a soliton or something like that. But in general, yeah, it's not so clear.
Is there an example with non-vanishing first-chain class where you can verify the conjecture?
Yes. Yeah. Well, I guess, yeah. So I think I mentioned at some point last week or something, we have this work with Yuri and Vesti, like in toric situations where we are verifying this conjecture, yeah, for a general like toric Fano, generalized Kähler structure, like symplectic type. So what I mean is, yeah, like a generalized Kähler structure of symplectic type on toric Fano background. But I guess there are others as well. So I also have this result with Manchun Lee, where if you assume some kind of negative curvature condition, some kind of, if you assume that there's a background metric satisfying a certain kind of negativity of curvature, then you can get the long time existence of the flow. And that's a situation too, where kind of to get a reasonable limit, the natural thing to do is to sort of blow down, but then this can produce singularities. This produces singularities at infinity, like for Kähler-Ricci flow. And then there are some of these, so there are also cases of this generalized Kähler-Ricci flow of commuting type, which again, I'll eventually get to this, where you can prove the conjecture and it's a finite existence time. Yeah. But so yeah, it's these are all good questions. Yeah, so I guess next time maybe my plan was maybe it's good we got these statements out. So next time I want to discuss more or less the full proof of Zhao's theorem to try to just sort of explain maybe a little bit more like why I was saying a few weeks ago about this sort of holy grail of the potential and sort of the way the potential enters the analysis to sort of get these estimates and then prove this theorem and then after that I mean I still haven't talked about the generalized Kähler setting at all and then after that move to generalized Kähler-Ricci flow. So yeah, any other questions?
Maybe one thing. So, what's a good example of? So, presumably there has been a lot of study of Kähler-Ricci flow in the case of these threefold singularities like flips and conifold transitions.
Yeah.
Do you like what is the what's the basic phenomenon? Do you remember what it's supposed to do?
I think I probably better not say anything
Okay.
about that. I mean, just because I don't think I would probably say it correctly. But I think maybe I just say that I think it is verified, well, that those transitions which you mentioned, I think can occur. I think it's been verified as a phenomenon in the sense that like examples have been given to show that it can do this.
Mm-hmm.
Although again, it's I don't want to speak out of turn, but like I think
who did that?
Yeah,
that
right. So this is all in the work of Jan Song. So he's and many co-authors, and I guess other people have contributed as well. But I think he's sort of mostly it's him and co-authors working on this. And yeah, I think there are like sort of expectations that maybe every singularity can be described in a certain way, but I think it's mostly in terms of phenomenology, like it can be shown to occur, but even that maybe requires some choice of what it means to extend it beyond a singularity. Right? So this of course requires a lot of analysis, to make sense of that. But yeah, I mean, if you have some idea about some kind of different algebro-geometric singularity that should occur, this would of course be an amazing thing to see or to try to construct. Yeah. So okay, yeah. Thanks everyone. Well, I guess I'll see you next week.
Thank you.
Thank you.
Thanks, Jeff.
Sure.
Thanks a lot.
Thanks. Bye.
Bye.